In 1925, Bucyrus Erie made a decision that would change mining forever. They began wiring their largest excavators directly to the grid. As machines scaled into the multi-megawatt range, electric rope shovels and walking draglines outgrew what onboard engines could practically deliver. While other manufacturers were building bigger diesel engines, Bucyrus was plugging their machines into the power grid like giant appliances. The result was multi-megawatt machines that moved immense volumes of earth more efficiently than any comparable diesel setup. This is the insane truth about how Bucyrus Erie used megawatt power to silence diesel engines, only to then be silenced themselves by Caterpillar's $8.8 billion acquisition. The story begins in 1880 in Bucyrus, Ohio, when Daniel P. Eels and partners founded the Bucyrus Foundry and Manufacturing Company. Their first products were simple steam-powered excavators designed for railroad construction and canal digging. These early steam shovels used coal-fired boilers to power mechanical systems through chains, gears, and cables. In 1927, Bucyrus merged with the Erie Steam Shovel Company of Erie, Pennsylvania, creating Bucyrus Erie. This merger brought together two complementary technologies: Bucyrus's foundry expertise and Erie's advanced steam shovel designs. The combined company immediately began pushing the boundaries of excavator size and capability. The real transformation came in the 1920s when Bucyrus Erie recognized that steam power had fundamental limitations. Coal-fired boilers required constant fuel supply, generated inconsistent power output, and needed frequent maintenance. More critically, as mining operations grew larger and moved deeper, the logistics of supplying coal to remote locations became prohibitively expensive. Bucyrus Erie's engineers made a radical decision: abandon steam for electricity. In 1925, they introduced the 120B mine and quarry shovel. From there, electric power rapidly became the norm on larger units, fed by trailing cables that eliminated onboard fuel and unlocked far more usable power. The electric conversion solved multiple problems simultaneously. Electric motors provided instant torque at any speed, unlike steam engines that needed time to build pressure. They ran continuously without fuel breaks, increasing productivity. Most importantly, they could scale to enormous sizes without the weight penalties of large boilers and fuel storage. By 1930, Bucyrus Erie had established the template that would define their identity for the next 80 years: massive electric rope shovels and walking draglines powered by grid electricity. Their 1950B class rope shovels, introduced in the 1960s, worked with about 105 cubic yard buckets on machines like the Silver Spade, and up to roughly 130 cubic yards on sister units such as Gem of Egypt. Walking draglines represented Bucyrus Erie's most spectacular achievement. These machines moved on massive steel shoes that lifted the entire machine and walked it forward in 6-foot steps. The largest, the 4250W Big Muskie, stood about 22 stories tall and weighed roughly 27 million pounds. It could move hundreds of tons per pass with a 220 cubic yard bucket, roughly 20 highway dump truck loads in a single scoop. The shift to grid power changed the economics of big digging. Electric rope shovels and draglines work through long shifts without refueling stops, and with far fewer engine-related service intervals. That steady operation raises availability and output compared with diesel machines doing the same job. In high-volume mines, the extra hours translate into more tons moved and a lower cost per yard. The engineering challenges of scaling electric equipment were immense. The 3850B stripping shovel, commissioned in 1962, used roughly a 210 to 215-foot boom to reach across large strip mines, swinging a dipper of about 115 cubic yards. The boom alone handled massive loads, demanding specialized high-strength steels and advanced welding to survive the stresses. As machines grew larger, power delivery had to scale. Some sites used multiple high-voltage feeds to distribute load safely. Others, like Big Muskie, drew 13,800 volt power through a single trailing cable system. The machine's electrical room was packed with transformers, switchgear, and control equipment. As machines scaled into multi-megawatt loads, electric rope shovels and walking draglines became the flagship class. Diesel engines kept advancing, but the largest excavators drew their power from the grid rather than from onboard engines. Bucyrus-Erie didn't abandon engines entirely. Diesel power stayed essential wherever machines had to move. That's why the biggest diesel footprint was in rotary blast hole drills, smaller shovels, and site support equipment. Blast hole drills represented the largest category of diesel-powered Bucyrus equipment. These machines needed to move frequently around mining sites, drilling precise patterns of holes for explosive charges. Bucyrus's 49 series rotary blast hole drills were offered in diesel or electric configurations. Diesel builds commonly used high-output industrial engines from Detroit Diesel, Caterpillar, or Cummins. Portability was crucial for blast hole drills because mining operations required thousands of precisely positioned holes across vast areas. A typical copper mine might need 15,000 blast holes annually, each positioned according to geological surveys and blast patterns. Trailing electrical cables would have made this impossible, so diesel power was the only practical solution. The 59 series rotary drills showed the upper end of diesel-powered drilling, and like the 49 series, they were built in diesel or electric configurations to suit site needs. Support equipment around the pit also relied on diesel engines. Service vehicles and water trucks typically came from other OEMs, and large haul trucks associated with Bucyrus arrived via later acquisitions, most notably Terex Mining's electric drive trucks in 2010. Smaller rope shovels, typically under 15 cubic yard capacity, often used diesel power for increased mobility. These machines worked in smaller mines or performed specialized tasks where electrical infrastructure wasn't available. The 195HR hydraulic shovel used a Cummins diesel engine and could be transported between job sites on standard lowboy trailers. The boundary between diesel and electric power was clearly defined by duty cycle and scale. Diesel worked for equipment that moved frequently, operated in remote locations, or needed quick deployment. Electric power dominated where machines operated continuously in fixed locations with high power demands. Operators valued diesel equipment for its independence and flexibility. A diesel machine could begin working immediately upon arrival at a new site, while electric equipment required substantial infrastructure investment. Fuel could be delivered anywhere, but electrical substations required months of planning and construction. Parts commonality was another advantage of diesel power, and because many Bucyrus diesel machines used engines from the big makers, operators could maintain parts inventories that served multiple equipment types. Electric machines required specialized components that only Bucyrus could supply. Portable rotary drills mounted on mobile carriers exemplified the diesel approach. Quick to reposition across the pit, and fast to set up at new hole locations. At mega-scale, electric wasn't just preferable, it sidelined onboard diesel. Multi-megawatt loads, steady torque, and fewer service stops made grid-fed machines the rational choice. As Bucyrus-Erie pushed machine sizes beyond anything previously imagined, the limitations of diesel power became insurmountable. Power requirements scaled exponentially with machine size. A 100 cubic yard electric shovel required approximately 6,000 horsepower, equivalent to 8 large diesel engines. The weight of diesel engines, fuel tanks, cooling systems, and exhaust equipment would have added hundreds of tons to already massive machines. More critically, diesel engines couldn't provide the consistent power output needed for continuous heavy-duty cycles. The 4250W walking dragline, introduced in 1969, carried a 310-foot boom and a roughly 220 cubic yard bucket, showing the practical limits of the class. At the top end, multi-motor electric systems controlled hoist, drag, swing, and walking, capabilities that would be impractical with onboard diesel power at that scale. Grid power provided several advantages impossible to achieve with onboard generation. Electrical utilities could supply virtually unlimited power, allowing machines to operate at full capacity continuously. The power was also remarkably consistent. Grid voltage rarely varied more than 5%, while diesel engines experienced significant power fluctuations under varying loads. Maintenance requirements differed dramatically between electric and diesel systems. Electric motors contained few moving parts and could operate for years without major service. Diesel engines required oil changes every 250 to 500 hours, filter replacements, fuel system maintenance, and periodic overhauls. On a machine operating 6,000 hours annually, these differences translated to weeks of additional uptime for electric equipment. The cost per cubic yard moved heavily favored electric power at large scales. Electricity typically cost 8 to 12 cents per kilowatt hour, while diesel fuel cost $2 to $4 per gallon. A large electric shovel might consume 4,000 kilowatt hours per day, costing $400 to $500 in electricity. An equivalent diesel machine would burn 800 to 1,200 gallons daily, costing $2,000 to $4,000 in fuel alone. Environmental considerations also favored electric power in large mining operations. Diesel engines produced significant emissions that accumulated in open pits, creating air quality problems for workers. Electric machines produced no local emissions, improving working conditions and reducing regulatory compliance costs. By the early 1980s, newer draglines and shovels adopted AC drive systems that replaced large DC motor generator sets, improving efficiency and heat management. Power factor correction became critical as machine sizes increased. Large electric motors drew reactive power that utilities charged for separately. As machines grew, mine power systems added substations, switching, and power quality measures to feed continuous high loads and manage utility charges. Where grid access was limited, temporary generator sets could feed a shovel or dragline, but the prime mover still wasn't mounted on the machine. By 2000, Bucyrus International had grown from a regional manufacturer into a leading supplier of large mining equipment. The company had systematically acquired competitors, absorbed their technologies, and built a comprehensive portfolio spanning electric shovels, draglines, rotary drills, and support equipment. The consolidation began in earnest during the 1990s mining boom. Bucyrus acquired Marion Power Shovel in 1997, gaining access to Marion's legendary dragline technology and established customer relationships. The $400 million deal eliminated Bucyrus's primary competitor in the walking dragline market and added Marion's 8,000 series machines to their product line. Marion brought more than just products to the merger. The company's engineering team had developed advanced computer modeling techniques for dragline design, enabling larger machines with improved reliability. Marion's 8750 dragline had established new standards for bucket capacity and reach, technologies that Bucyrus immediately incorporated into their own designs. In the 2000s, Bucyrus expanded through targeted deals, most notably the 2007 acquisition of DBT and underground mining, and the 2010 purchase of Terex's mining business, which added hydraulic shovels and large mining trucks. These deals broadened Bucyrus's portfolio into underground systems, hydraulic shovels, and large trucks, while in electric rope shovels, Bucyrus and P&H remained the two principal suppliers worldwide. The acquisition strategy continued with smaller deals targeting specialized technologies. Industry consolidation also reshaped drilling when Ingersoll Rand's Drilling Solutions business was sold to Atlas Copco in 2004. Each acquisition brought valuable technology and customer relationships. The DBT deal expanded longwall and room and pillar systems in underground mining, while the Terex mining purchase added O and K hydraulic shovels and unit rig electric drive haul trucks to round out the surface portfolio. By 2010, Bucyrus had assembled the most complete portfolio of large mining equipment in the industry. Their product line included electric rope shovels up to 120 cubic yards, walking drag lines up to 180 cubic yards, rotary drills capable of 18-inch holes, and haul trucks up to 400 tons capacity. More importantly, they had built a global service network supporting thousands of machines in active operation. This comprehensive portfolio made Bucyrus an irresistible target for Caterpillar, which had dominated construction equipment but struggled to penetrate large-scale mining. Cat's mining division generated only $5 billion in annual revenue compared to $20 billion for construction equipment. The company needed mining expertise, established customer relationships, and proven large-scale technologies. Caterpillar's interest intensified during the 2008 to 2010 commodity boom when mining companies invested heavily in new equipment. Iron ore, copper, and coal prices reached historic highs, driving demand for the largest possible excavation equipment. Bucyrus's order backlog swelled to $8.8 billion, representing nearly 3 years of production. The acquisition negotiations began in late 2010, with Caterpillar initially offering $68 per share for Bucyrus stock. Bucyrus management rejected the offer as inadequate, leading to a bidding war that ultimately reached $92 per share. The final deal, announced in November 2010, valued Bucyrus at $8.8 billion, including assumed debt. Caterpillar's motivation was strategic rather than financial. The company wanted immediate access to Bucyrus's technology, particularly their electric drive systems and large-scale engineering capabilities. Cat also coveted Bucyrus's installed base of over 10,000 machines worldwide, representing a captive market for parts and service worth billions annually. The deal faced regulatory scrutiny in multiple countries due to its size and market impact. The European Union required Caterpillar to divest certain underground mining equipment lines to maintain competition. Similar conditions were imposed in Australia and Canada, where Bucyrus held dominant market positions. The integration began immediately after the July 2011 closing. Caterpillar rebranded all Bucyrus products with Cat model numbers and yellow paint schemes. The iconic Bucyrus name disappeared from new equipment, ending 131 years of independent operation. Engineering teams were consolidated into Cat's mining division, and manufacturing was integrated into Cat's global production network. The acquisition proved transformative for Caterpillar's mining business, elevating Cat to the top tier of global mining equipment manufacturers. The company gained immediate credibility with major mining companies and access to projects requiring the largest possible equipment. For the mining industry, the Bucyrus acquisition marked the end of an era. The company that had pioneered electric mining equipment, built the world's largest excavators, and defined the technology standards for surface mining had been absorbed into a larger corporate entity. The machines continued operating under Cat colors, but the innovative spirit that had driven Bucyrus for over a century was now channeled through Caterpillar's corporate structure. The yellow machines working in mines today still carry Bucyrus DNA in their electric drive systems, structural designs, and operational software. Big Muskie may have been scrapped in 1999, but its technological descendants continue moving mountains under the Caterpillar banner, testament to the engineering excellence that made Bucyrus Erie the undisputed king of large-scale mining equipment.